a brief review on mechanical vibrations. Motion of a particle or body that oscillates about a position of equilibrium. Most times it is undesirable. We are limiting our discussion to 1 degree of freedom, 1 DOF. What is the period? The period is the time interval required for the system to complete a full circle of motion. Frequency is the number of circles per unit time. Amplitude is the maximum displacement of the system from its position of equilibrium. When motion is maintained by restoring the forces only, the vibration is said to be free. That is when the motion is maintained by the restoring forces only. Vibration is said to be free. When a periodic force is applied to the system, it is said to be a forced vibration. It is undamped if we neglect the effect of friction. But all vibrations are actually damped in reality because friction exists. The amplitude of vibration is affected by the magnitude of the damping forces. Okay. So if we want to look at vibration without damping, this is how we approach vibration without damping. First, we consider a particle. This is the weight acting downwards. This is the tension, which is equal to the K times the static deflection when the spring is at equilibrium. This is when it's unstretched. This is when it's stretched. Okay. So this setup is at equilibrium. So we can write that at equilibrium, the weight from this diagram is equal to K extension, static extension. Now we consider when we stretch the spring by an additional distance x. So we consider that case now. Spring again. Okay. This was at equilibrium position, and this is when it's stretched by x. The tension will therefore be K, the static extension plus this x extension, and this is the weight acting, and the weight is equal to ma which is equal to m double dot x. Okay. The acceleration. Okay. So we can write that f is equal to w minus k static extension plus x. This will leave that f is equal to minus kx, and we know that f is also equal to mx double dot, therefore mx double dot plus kx is equal to 0. And this equation of motion has the solution of the form x equal to c1 sine k over m root t plus c2 cos root k over m. X is a periodic function of time and represents a vibration of particle p. Okay, and we know that we can write omega n to be, which is the natural frequency, to be equal to the root k over m. Furthermore, we can write this equation to be x is equal to c1 sine omega nt plus c2 sine cos omega nt. X double dot plus omega n square x will be equal to 0. We obtain this equation by dividing through by the mass, dividing through by mass, I can write the velocity by differentiating the distance once, and that will give me and I can get the acceleration by differentiating twice or differentiating the velocity once. Either differentiating the distance twice or differentiating the velocity once. That will be the initial condition of motion can be determined by solving this constant C1 and C2 can be determined by solving this equation with initial conditions. U1 is equal to 0 if the particle is displaced from its equilibrium position and released at t equal to 0 with no initial velocity. C2 is equal to 0 if the particle starts from 0 position at t equal to 0 with an initial velocity. Okay. We can also write a simple harmonic motion of P by projecting on the axis the motion of a point describing an auxiliary circle of radius fm with a constant angular velocity. If we take that, we can write that x is equal to xm sine omega nt plus phi. That is, x dot will now be xm omega n cos omega nt. cos omega nt plus phi. And x double dot, the acceleration becomes minus xm omega n square sine omega nt plus phi. Xm is the amplitude of vibration, and phi is the initial position of Q on the circle. Initial position of Q on the circle, called phase angle. It's called the phase angle, the phi. Then the period is equal to tau n, which is 2 pi over omega n. So we can therefore draw our natural frequency diagram. Try to draw it like this. We have this, a point Q. The resultant of C1 and C2 this is P, this is point O, this is minus XM, this is XM, this is omega NT, this is phi. So we start from this point. Okay. Okay. Take that curve once again. This is X. This is X. This is T. This is tau. Okay. So natural frequency Fn is equal to 1 over tau n, which is equal to omega n over 2 pi in hertz. And 1 RPM is equal to 1 over 60 hertz, or seconds to minus 1. One RPM because revolution per minute, and there are 60 seconds in a minute, therefore 1 over 60. And tau n, Fn, omega n all depend on mass and k, but not on initial position. Or weight. or G. We can then write V max is equal to xm omega n. A max as maximum acceleration is equal to xm omega n squared. We can approximate the simple pendulum. An approx of simple pendulum. We will see where we do this approximation. Consider a simple pendulum, theta, L, and the path. We can write normal tangent, normal and T, MA T. Okay. So if we do the summation of the forces in the T direction, summation of forces in the T direction is equal to MA T, and that is minus W sin omega is equal to ML theta double dot, where this represents the acceleration. So we can write that theta double dot is equal to theta double dot plus G over L sine omega sine theta is equal to 0. Now this is where we do the approximation. We equate this to theta. We are assuming that theta is so small that the sine of theta and theta itself are not different. Therefore, we can have that theta double dot plus G over L theta equal to 0. And then we can write the equation theta is equal to theta m sine omega nt plus sine, and tau n is equal to 2 pi over omega n, which is equal to 2 pi root L over G.